For a modern mechanical watch, the most pressing threat is completely unseen. Our daily environments are saturated with invisible waves of distortion, magnetic fields generated by smartphones, laptops, and speakers. If you expose the delicate steel oscillator spring inside a traditional mechanical watch to these fields, the metal magnetizes. The coils cling to each other, immediately disrupting the watch's temporal accuracy. Historically, the peak of horological defense against this problem was the Rolex Moghaus. Its design relies on a traditional shielding methodology. Engineers wrapped the entire internal movement in a soft iron inner case, essentially building a miniaturized Faraday cage to absorb and redirect the incoming magnetic forces. While effective, this spatial armor requires compromise. The watch must be heavily built, with a thick metallic caseback that hides the intricate mechanics from the wearer. Omega engineered an entirely different philosophy. Instead of building a thicker shield to deflect the threat, they decided to remove the target. They systematically dismantled the traditional architecture of the watch, replacing every ferromagnetic spring, gear, and axis with rigid, non-magnetic material substitutes. The result is a mechanical movement capable of withstanding 15,000 Gauss of magnetic force. You could place the watch inside the active magnetic field of a standard MRI scanner without affecting its rhythm. Because there is no internal iron cage required for protection, the watch features a completely transparent sapphire glass caseback, leaving the mechanics fully exposed. Omega bypassed the limits of traditional metallurgy by abandoning it in favor of semiconductor physics and amorphous materials. This split-screen analysis shows exactly how these two competing architectures process magnetic flux. Watch the flux line striking the left side. The soft iron Faraday cage absorbs the magnetic energy, routing the invisible lines around the outer perimeter to protect the delicate center. Now look at Omega's solid-state substitution on the right. With the shield removed, the magnetic flux lines pass cleanly through the internal gears. Because the material's magnetic permeability is strictly zero, the parts do not interact with the force. Engineering components that cannot interact with magnetic fields offers a path to protection without the weight and visual limitations of internal shielding. Even without magnetic interference, a watch movement still faces constant mechanical wear. Here, a traditional metallic balance spring is expanding and contracting inside the case. This microscopic cross-section details the structural reality of standard metallic alloys. They are polycrystalline, built from microscopic, chaotic crystal grains smashed together, separated by jagged grain boundaries. Under the constant cyclical loading a spring endures, mechanical stress concentrates exactly at these boundaries. They illuminate as red stress points, gradually tearing open into microscopic fissures. Over time, these grain boundaries cause standard metallic watch springs to succumb to fatigue, eventually losing the elasticity necessary for precision. To solve for metal fatigue, Omega integrated silicon, specifically Si-14. This high-purity silicon wafer is the exact same foundation used to print modern computer CPUs. Silicon has different physical properties. It is a single crystal material, forming a flawlessly repeating grid of atoms extending uniformly in all directions. Because this lattice lacks internal grain boundaries to harbor stress, it is far less susceptible to fatigue than metallic alloys, retaining its structural integrity over millions of cycles. The manufacturing challenge is high. Standard metallic drill bits and lathes cannot machine single crystal silicon. The force would cause it to shatter like glass. Omega imported a manufacturing process called deep reactive ion etching. They used directed plasma to carve these nanoscale spring geometries out of the solid wafers, avoiding physical blades. By treating the mechanical oscillator as a semiconductor fabrication challenge, Omega achieved a highly resilient mechanical heart. Beyond the internal mechanics, the exterior diver's bezel is a high-impact zone. It requires an interface that marries scratch-resistant ceramic with visible metallic numerals to survive impacts against elements like a jagged reef wall. Traditional molten metals shrink dramatically as they cool. If you pour liquid steel into rigid ceramic, it pulls away from the edges, failing to bond cleanly into the microscopic pores. Omega engineered an intermediate material known as liquid metal. It is a specific bulk metallic glass formulated from titanium, zirconium, and copper. Liquid metal is an amorphous alloy, meaning it completely lacks a rigid crystal structure. Because of this, it does not strictly melt. At roughly 150 degrees Celsius, it simply softens into a viscous state. allowing engineers to press it directly into the sharp negative spaces of the ceramic. During the cooling phase, the amorphous metal solidifies exactly where it sits. It hardens flush against the ceramic with zero gaps, creating a fully continuous surface. Because this composite lacks crystalline borders, the resulting interface is highly resistant to chemical corrosion and measures mechanically 3 times harder than standard titanium. When you assemble these microscopic elements, you get the modern Omega master chronometer. Its operational resilience relies on non-magnetic solid-state substitution, a fatigue-resistant single-crystal silicon heart, and gapless amorphous metallic bonding on the exterior. High horology is often described strictly as the traditional art of polishing and finishing steel gears by hand. Omega proved that the limits of traditional metallurgy can be surpassed by integrating the properties of semiconductors and amorphous alloys.